Hi folks, welcome to the next lecture, and in this lecture we're just taking an introduction to probability. So before we start, we're just going to take a look at one of the foundations of probability. It's the fundamental principles of counting. There's two of them. They might seem a bit obvious, but we'll take a quick look. The first fundamental principle of counting states when there is one operation with n possible options and another operation with m options. The key word here is and. When we have n and m options, there will be a total of n multiplied by m. It's a bit of a mouthful, but we'll take a look at an example. So if a password has a single letter and a single digit, D6, K1 or 7, there's 26 options for the letters. There's 10 options for the digits. So in total, there's 260 possible combinations from one letter followed by one number. So the main thing is when you see the word and, we multiply. Looking at another example. Access code to a security system has 5 digits. Each digit can be 0 through to 9, so there's 10 options. How many codes are possible if each digit can be repeated and if each digit can only be used once? If each digit can be repeated, well, we have a choice of 10 each time. 10, so the first number we have choice of 10, and the second number, and the third number, and the fourth, and the fifth. So we have 100,000 codes, 10 to the power of 5. If we're not allowed repeat digits, then we're allowed 10 for the first number, but we're only allowed 9 for the second because we've used up one number, we can't repeat it. 8 for the third, 7, 6, and again we multiply. Now this significantly reduces the number of codes. As we can see, nearly less than 1/3. But that's the fundamental principle of counting one. If you see the word and, we multiply. First number and second number and etc. The second fundamental principle of counting nearly seems too obvious that it doesn't need stating, but it kind of does. So again, we have n and m options, but in this case, we're looking for n or m. If you see the word or, we add the number of options. So we take a look at an example. How many students are fluent in French or German? So in this case, we're simply saying, well, how many students are fluent in French? There are 8. Or German, there are 3. When we see the word or, we add. So 11 students are fluent in French or German. Now I know it seems really obvious, but just bear with me. We build on this in the second lecture. So now we just take a look at probability in general. So we're going to look at a kind of a coin being flipped twice. So determine the probability of throwing 2 heads or of throwing a head and a tails. So often the best way you can do this is draw a table which really illustrates all the possible outcomes. And here we have all our outcomes here, all the possible combinations. And once we have this, we can see, well, there's 4 possible outcomes. 2 heads is only one of those. So the probability of throwing 2 heads is 1 over 4. What's the probability of throwing a head and a tails? Well, here's a head and a tails, and here's a head and a tails in either order. Well, there's two of them, so that's 2/4, or probability of a half. We'll define probability a little bit more formally in a little while. So from this kind of quite simple little model for just two flips of a coin, very quickly scientists started to use the exact same logic for looking at genetics and how people inherit characteristics from their biological parents. So I'll take a quick look at one of these and then we'll move on, because obviously this is a huge field. So we take a look at the genetics of earlobes. So essentially, people inherit either attached or detached earlobes from their parents. So we get one gene, a pairing of genes. We get one from the mother and one from the father. And there are just two different versions of this gene. They're known as alleles, represented with a small e and with a capital E. So your parents have two of these in any combination, and then you get one each of these off each parent. So if you inherit two small e's, then you'll have attached earlobes. So because of this property, the small e form is said to be recessive, because you need two of them. And basically, no big E. The big E is the opposite. Big E is dominant. And what that means is if that's present in a pair at all, then that person will have detached earlobes. So with the recessive, you need both. With the dominant, you just need one of the you need both the recessive to have attached earlobes, and you just need any one of the dominant and you will have detached earlobes. So this is the way genetics works. I am not claiming to be an expert on genetics. Let it be recorded, put down in recording. So we get one earlobe gene, one allele from each parent. Parent can't pass on an allele that's not in their own pairing. And each allele is equally likely to be passed on. So this is now a similar table that we looked at for the coin toss. But now we have the father's alleles. Again, the father could have EE and the mother could have EE. So there's any amount of combinations could be. I just took a look at this with both parents having detached earlobes if you were to look at them. Not very good at drawing, I leave that. And we can see then that the likelihood in this scenario of a child having detached earlobes is 3/4. So that's the probability. The likelihood of a child from an offspring of these parents having attached earlobes is 1/4. And I'm going to leave it there. We could start to change these and take a look at different probabilities, but it's a whole world in itself, and we could kind of disappear down the rabbit hole and not reappear for a long time. And unfortunately, it's just beyond the scope of the module to kind of explore any further at the moment anyway. So now we're going to take a look at the main types of probability that are out there. There's actually a few of them. There's classical probability. This is kind of based on belief, where you make an assumption that a fair coin has a 50% of revealing a head or a tail when flipped, or that a fair dice has a 1 in 6 chance of turning up a 6 or a 1 when thrown, etc. It's kind of based on belief that logically this is what should happen. There's empirical probability, which is based on an experiment. You could start flipping a coin and recording the results. And then over time, the law of large numbers, over time, with repeated experiments, the empirical probability should tend towards the classic or the theoretical probability. This is sometimes called the theoretical probability as well. So empirical is where you actually start to do something. You're using you're doing an experiment again and again. Medical trial is an example of these, where thousands of patients are given a drug, and then kind of it's seeing how many of them develop any side effects, or if side effects of any nature. Then there's the kind of new kid on the block, so to speak, very much viewed with suspicion for a long time, but now becoming very mainstream, is what's called subjective probability, sometimes called Bayesian. And this is basically probability which are based on someone's judgment, usually somebody who's experienced in whatever is being judged. But we'll take a look at them each briefly in turn. In all the maths we'll be doing, we'll be looking at classical probability, but just as scientists, you have to be aware of the other types as well. So classical is really where each outcome is equally likely to occur. And what we have is the number of favorable outcomes over the total number of outcomes. So just to give an example, if a dice is rolled, find the probability of rolling a 5. Well, in this case, there's 6 possible outcomes. How many 5s is there? There's only one 5. So the probability of this event, E, we'll talk about the language in a little bit shortly. So actually we would say, because the event in this case is rolling a 5, so we would say the probability of rolling a 5 is 1/6. The probability of rolling an even number, well, there's 3 even numbers on a dice. There's the 2, the 4, and the 6. So there's 3 desirable or favorable outcomes, and there's 6 possible. So the probability of throwing an even number is a half. So that's the idea of classical probability. We could talk about pulling a card. What's the probability that you draw a card from a normal deck of cards? There's 52 cards in a normal deck. What's the probability of drawing a 2? There's 4 2s. So the probability of drawing a 2 is 1/13. And this, like I said, this is just part of the language, PE, the probability of an event occurring. Often you write the event in there as well. This is just like we were saying, 2, I should have sequenced these in, but it didn't happen. Find the probability of at least one head appearing. Well, at least one head, we'll actually stop here. So another example of classic probability. Sorry, I'm stuck. If we toss 2 coins again, we're familiar with this. Find the probability of at least one head appearing. Well, first kind of say we talk about the sample space, and like I was saying, one way to find the sample space, that's the possible outcomes. So sample space, again, I'll talk about these in a little bit, but that's the possible outcomes. One way to do it is to draw the table exactly like we did previously, etc. TH and TT. And that defines the sample space. So there's our 4 possible outcomes. How many of these outcomes are favorable to at least one head? Well, there's a head, there's a head, and there's a head, at least one head. 3 of them are favorable. So this is now our favorable outcomes. This is our sample space. So the number of favorable outcomes, NE over NS is how it's, NS is how it's written. favourable over possible, and that gives us 75%. Now we look at empirical probability. This is more kind of doing an experiment again and again. Assumes an experiment can be repeated many times. When we say experiment in terms of probability, we're talking about something like tossing a coin, drawing a card from a deck, rolling a dice. Those are experiments, not kind of your natural scientific experiment. So in this case, what we do is, rather than kind of figuring it out as we did in the classical way, where we go, okay, there's 6 sides to the dice, there's 1 5, so 1 over 6 is the probability of throwing a 5. What we do now is we actually just start rolling the dice. Roll it 10 times. How many 5s do I get? Roll it 100 times. How many 5s? Roll it 1,000 times. Roll it 1,000,000 times. And the idea is then, with the law of large numbers, is that the larger number of repetitions you complete, the closer this value will get to the theoretical or the classic value. But often this is the only way you can go. Like, sometimes if you're doing something that hasn't been done before, you can't really figure it out. You have to do experiments to see. So medical trials of drugs often use very large numbers of people to try and so we do large numbers of trials to try and pick up some side effects that might only have very low probabilities of occurrence, because obviously that's very important from a drugs trial point of view. So medical trials would certainly be empirical probability trials. Oh, this has come up the wrong order. I'll speed through it. Sorry, this has come up all the wrong order, but I'll just talk through it. Salesperson knows from years of experience, so this is his this is all the repetitions. So he knows that 3 out of 10 calls will result in a sale. So the empirical probability that the next phone call will result in a sale is 0.3. If we took a sample of results, so again, this isn't somebody sitting down and saying 15% of students should get an A in the classical sense. This is more, well, we've done 1,000 experiments. 1,000 students have sat the exam. 15% of those have got an A. So the empirical probability is that the next student, or a student drawn randomly from that lot, got an A, would be 0.15. With sports statistics, again, the passing average of a top football player, that can be used to predict, well, what's the probability that their next pass will be successful. So these are all examples of kind of empirical probability. We won't really be working with this. We'll be staying with classical. And then there's the subjective approach. So the subjective approach kind of results from intuition. So this is really where the classical approach isn't possible, because it's never really happened before. And there's no history of outcomes, so we can't rely on kind of old experimental results to try and figure out what's going to happen. So usually it's about trying to get kind of an expert's opinion, somebody who knows the field of the event we're examining, and we ask them, like, what would you think? And then you might get several experts and kind of slowly gather the probabilities that way. So just some examples are written here. A business analyst figuring out what's the probability of a certain union going on strike. Again, that's not something you could really look up, It'd be more kind of in the current climate, etc. You'd need somebody who understands what's going on. An engineering predicting the probability of a nuclear meltdown in a certain reactor. He'd have to, obviously this engineer would know the reactor and any quirks of its kind of its operation. Or a sports pundit predicting that a particular team would win the Premier League in any season. These are all subjective probabilities. But the main thing is that the person who's making the subjective judgment is cognizant of the field. It's not just a random person. This is the key to all of this. That's why it was so reluctant to be accepted into the branch of mathematics, because it was subjective. Like, so a lot of mathematicians kind of rejected this approach for quite a while. So this approach is very important in medicine. Like any kind of a doctor's opinion is kind of a subjective probability. Oh, I know this patient, he's been in, 40 times before. I know he smokes, he's got a cough. So the doctor is making his assessment based on what he knows. Like, there's no way a patient could Google that information about somebody. It's more an expert's opinion on it. So I'm not going to get caught up in subjective either. Again, we won't be studying. It's not really, again, it's more advanced. It's much more advanced than we're kind of able to in this short module. It'd be more if you were studying kind of mathematics and certainly kind of third level maths at a fairly high kind of, you'd be studying maths pretty at a pretty deep level, which we're not. So now we're just going to look at some definitions. I've been mentioned a few of these just to formally define them. Sorry, my tongue is tripping over itself at the moment. A trial is the operation being observed. So the tossing of a coin, that's an example of a trial. The rolling of a dice, the drawing of a card, the picking a student at random from a group. An experiment is the number of trials being observed. Sorry. The coin is tossed 400 times. So that's the experiment. The sample space is all the possibilities, the set of all possibilities that can occur as a result of this. So in the coin tossing scenario, there's two outcomes possible. And an outcome is essentially each element in here. So there's two outcomes, each of heads and tails are both outcomes. So the sample space would have two outcomes, and then we can list each outcome as heads or tails. Finally then, an event is a chosen outcome, favorable, desired. There's lots of different words. You might choose heads, you might choose tails. How many tails, etc. What's the probability of throwing tails? So the classic rule for determining probability: number of favorable outcomes over number of possible. And probabilities can be expressed on a scale of either 0 to 1 if we're using decimals, or 0 to 100% if we're talking about relative probabilities. If we're talking about probabilities in terms of percentages, then they're called relative probabilities. Usually we stay in this one, unless the question kind of suggests otherwise. So just to define it a little bit more formally, the probability of an event lies between 0 and 1. If an event cannot occur, its probability is 0. If an event is absolutely certain to occur, its probability of 1. If there's an even chance of something happening, then it's halfway along. It's got a probability of 0.5. The sum of probabilities of a mutually exclusive outcomes. We're going to come across mutually exclusive in the next lecture in more formal sense. Essentially, mutually exclusive means something can only be one or the other. So if we have heads and tails, if we're tossing a coin, our outcome can either be heads or it can be tails. It cannot be both. So their heads and tails are mutually exclusive. It's one or the other. The probability of two mutually exclusive events is 1, because when you flip a coin, it's either going to be heads or tails. It has to be one or the other. So the outcome there, the probability is 1 of throwing a heads or a tails. So now we'll just take a look at some kind of typical problems, and we'll finish up then So a person is asked which day of the week they were born on. What's the probability that they were born on a Sunday? Well, what's the possible? Remember, probability of an event. So in this case, we'd be saying probability of born on Sunday, just to be, I won't write them all out like this, but just to be, remember, it's favorable outcomes over possible. So when we start to fill in, well, how many days is possible? Well, there's 7 days of a week that a person could be born on. How many days are favourable, as in the ones we're interested in? Well, Sunday, there's only one Sunday. And then we could turn this into a decimal. I think it's 0. Just double check that. Sorry, that 8 should be a 9 when we round up. Card is drawn from a normal deck. What's the probability the card is a king? Well, again, what's the possible, which goes on the bottom? Well, there's 52 cards in a deck. On Moodle, I have a standard deck of cards laid out for you in the useful resources section, so you can kind of work, you can see yourself. Some people are very familiar with cards, other people not so familiar with cards. So rather than me explaining it here, just take a look on Moodle and you'll find all the information you need. So favorable is kings. Well, there's 4 kings. So the probability of drawing a king, always cancel if possible. And then when we work this out, 1 divided by 13 is 0.0769. 4 decimal places is enough, but be sure to round up correctly. What's the probability of drawing a diamond? Well, probability of a diamond. There's 13 diamonds in a deck. There's 52 cards in a deck. So the probability of drawing a diamond is 0.25. Because diamonds is one of the 4 suits of a card. What's the probability of drawing a red card? Probability of red. Well, 2 suits are red, so that's 26 cards. Diamonds and hearts. So what's the probability of drawing a red card is 0.5. And again, I know these might seem really obvious, but I'm just really laying down the foundation for how we approach probability for when things get trickier. So bunch of socks in a drawer. Sock is taken out at random. What's the probability it's white? Well, the probability of sock being white is 4, because there's 4 white socks. How many socks is there altogether? There's 16. So probability of drawing a white sock is a quarter, 0.25. Probability of drawing a red sock, 5 over 16. And when we work that out, (0.3125). And finally then, what's the probability of drawing a black sock? Seven of them in the drawer. This sounds a lot like my sock drawer. Again, that's not going to simplify. And when we work this out, we get 0.4375. Now if we add up all of these are all mutually exclusive. A sock can't be black and red. Well, in this drawer it can't. So if we add up all these, they will actually add to 1. because we've covered all possible outcomes. So the probability of each outcome we've worked out, but now we've covered all possible outcomes, so those probabilities should add to 1. So we just take a look at odds now. I'm just going to take a quick look at one or two other types of probabilities, just to kind of help you use probabilities in daily life rather than more from a hard sums point of view. So say if Bluebell is odds-on favourite to win the race, and the odds are given as 9-4, and then there's Old Nag has odds of 20-1. What's the probability each horse will win? Probability that Bluebell will win is there's €4 will pay back 9. If you bet €4, the bookie will give you back 9. How you work out the probability is the 4 is the favourable, but then we add together the two numbers. So what's the probability that Bluebell will win is 4/13. Which is about 30.7. So we'd say 31%. So that's why Bluebell is the odds-on favourite. What's the probability that Old Nag will win? Well, Old Nag is 20-1. Again, we add together these, though. You add them. So now, when we work this out, and this is probably about 4.8%. We'll say about 5% again. I should really keep the decimals, etc. But that just allows you to give an idea from when you see odds, how do I work out the probability that a particular horse or a politician or whatever will win. One more just from terms of view, it might be obvious, but just in terms of frequency distribution. So the following distribution represents the ages of 30 students. What's the probability that a student selected at random is between 26 and 30? Well, what's the desirable? This is our event, their age. So there's 8 students that are favourable, that fill that category. In total, there's 30 students. So what's the probability that a student is in this age group? 8/30. And we can work it back to a probability then again like that. So just if you come across a frequency distribution, it's kind of pretty much the same technique, just a little bit more generalized. So we'll finish up there, guys. Thanks for listening, and we'll develop these techniques in the coming lectures then with a bit more detail. So thanks again. Chat to you soon.